We'll start in a minute. We'll continue with the final exam review. So just a reminder, the final exam opens early Monday morning, just after midnight on May 4th, and then it closes at before midnight at 11:59 p.m. on Tuesday, May 5th. The last 10 minutes today, I will give you an opportunity to log into Moodle and complete the course evaluations. Today is the deadline. If you don't do it now, then you have to do the evaluations before the end of the day today. Okay, one of the problems that we didn't get to on the sample final exam was this problem number 25, which I've reproduced here. So we have the graph of f of x, which is just the connection of two line segments, and I've labeled the ordered pairs -3, 2 up here on the upper left, down here -1, -2, and this one is the ordered pair 2, 4. And then noting that f of -3 equals 2, f of -1 equals -2, and f of 2 equals 4, those are consistent with the ordered pairs on the graph. So to get a graph of y equals f of x minus 2 from the graph of f of x, well, you can remember that this means to translate the graph of f of x 2 units to the left. But one way to explain that, note that the domain of f is from -3 to +2. -3 to +2 is the domain of f. So the domain of f of x minus 2 is not the same as the domain of f. So what we can do is we can write -3 less than or equal to x minus 2, which is less than or equal to 2, and then solve this compound inequality for x by adding 2 to all three parts. -3 plus 2 is -1, and x minus 2 plus 2 is x, and 2 plus 2 is 4. So this tells us that the domain of y equals f of x minus 2 is from -1 to 4. So we'll use what we know about the graph of f of x to get a graph of y equals f of x minus 2. So this is just the connection of two line segments. And also these equations will be used in this graphing y equals f of x minus 2. Okay, so down here we'll just create a table of x and y coordinates. So the smallest domain value for y equals f of x minus 2 is x equals -1. But remember what y is. Y is f of x minus 2. So when x is -1, this becomes f of -3. Because -1 minus 2 is -3. And if you remember, you can't see it, but from above, we saw that f of -3 is equal to 2. Okay, another point that we want, which is an endpoint to both line segments, this is going to occur when x is 1, and then the y-coordinate is f of 1 minus 2. 1 minus 2 is negative 1, so f of negative 1, and we saw earlier that f of negative 1 equals negative 2. And then finally, the largest domain value for y equals f of x minus 2 is 4. So when the x-coordinate is 4, the y-coordinate is f of 4 minus 2, but 4 minus 2 is 2. So the y-coordinate is f of 2, but we know from above that f of 2 is equal to 4. Okay, so we plot those points. Negative 1, 2 is this point. 1, negative 2 is this point. And 4, 4 is this point. And then we just connect the dots. So if you compare this graph with the one above, this graph is the graph above, translated horizontally 2 units to the right. So maybe the easy thing to do is just to remember that f of x minus 2 is the graph of f of x shifted 2 units to the right. But you can make sense of it analytically by going through this process. Okay, the next example, we're using the same function f of x as before, as in the previous example. So once again, f of negative 3 is 2, f of negative 1 is negative 2, and f of 2 is 4. And the domain is from negative 3 to 2. So for this new function, y equals the negative of f of x, notice that this one doesn't have any effect on the domain values. So the domain of y equals negative f of x is the same as the domain of f of x above. But what we're doing is we're taking the negatives of the y-coordinates of the function f of x. The graphical effect is a reflection across the x-axis. So we'll plot 3 ordered pairs again. Okay, this time the domain values are not affected. So when x is negative 3, y is equal to the negative of f of negative 3. But we saw earlier that f of negative 3 is 2, so the negative of 2 is negative 2. Then the next domain value that we'll consider is when x is negative 1. The y-coordinate is the negative of f of negative 1. Above, f of negative 1 is negative 2, so the negative of negative 2 is positive 2. And then finally, when x is 2, the y-coordinate for this function is the negative of f of 2. But f of 2 is 4, so the negative of 4 is negative 4. So we plot these 3 ordered pairs, negative 3, negative 2. So negative 3, negative 2. The next ordered pair, negative 1, 2, is right here. The third ordered pair, 2, negative 4, is down here. Then connect the dots. So if you compare this graph with the one above it, you can see that this graph is the reflection of f of x across the x-axis. So this gets reflected down here, this gets reflected up there, this gets reflected down to there. Okay, the next example. Okay, so we start with the same function, y equals f of x. This is the same as the previous two, but we want to graph y equals 2 times f of x. So for this new function, y equals 2 times f of x, the domain values are not affected. It's just that the y coordinates for this one will be 2 times the y coordinates of f of x. Okay, so this one is pretty straightforward. We'll use the same domain values, -3, -1, and 2. But this time y equals 2 times f of x. When x is -3, the y coordinate is 2 times f of -3. Remember that f of -3 is 2, so 2 times 2 is 4. When x is -1, the y coordinate for this function is 2 times f of -1. F of -1 is -2, so 2 times -2 is -4. And then when x is 2, the y coordinate is 2 times f of 2. F of 2 is 4, so 2 times 4 is 8 on this one. Okay, so we'll plot those ordered pairs, -3, 4. Just about right there, -3, 4. -1, -4. It's down there. And then 2, 8 is about here. And then we connect the dots. Okay, so this graph, you can tell that it's the graph of f of x stretched vertically by a factor of 2. So that's what this notation indicates. We're multiplying all of the y coordinates of f of x by 2. So the graphical effect is that it stretches vertically. Okay, a couple more. The next one, same function f of x as before. And we want to graph y equals f of x minus 1. So no doubt you know what's going to happen on this one. We're just going to subtract 1 from all of the y coordinates on f of x. The graphical effect is a vertical translation downward by 1 unit. So let's just go ahead and do it real quick. So the same x coordinates, -3, -1, 2, and y equals f of x minus 1. Okay, so this is the y coordinate is f of -3 minus 1. F of -3 is 2, and 2 minus 1 is 1. So the ordered pair -3, 1 is a point on this graph. And then when x is -1, the y coordinate of the new function is f of -1 minus 1. But f of -1 is -2, and -2 minus 1 is -3. So the ordered pair -1, -3 is a point on this graph. And then when x is 2, the y coordinate is f of 2 minus 1. F of 2 is positive 4. 4 minus 1 is 3. Okay, so we'll plot these points, -3, 1. This right here. -1, -3. 2, 3. Then connect the dots. So this graph is 1 unit lower than the graph of f of x. It's a vertical shift downward by 1 unit. Okay, those are the 4 functions that were on the sample final, but I'm going to do one more that's not on the sample final that might be useful for you to know. I've seen this particular type of problem on previous final exams. So we're starting with the same function, y equals f of x. And this time we want to graph y equals f of 2x. So on this one, this time the domain values are affected because it's f of 2x. So remember the domain of f. I'll just remind you of the domain of f. It's from -3 to 2. So the domain of y equals f of 2x is not the same as the domain of f. So how do we find the domain? Well, these numbers on the inside of the parentheses, the 2x values have to range between -3 and 2. So we write -3 is less than or equal to 2x, which is less than or equal to 2. And then we solve this inequality, this compound inequality for x. We'll divide all three parts by 2. So the domain of f of 2x is -3/2 to +1. Okay, but what we do next is similar. It's the same part of the process that we've been doing. We just might need to think a little harder on this one. Okay, so the smallest domain value for f of 2x is -3/2. So I'll pick -3/2 for the x value. And then the y coordinate is f of 2 times -3/2. But 2 times -3/2 is -3. So f of -3, we know that that's equal to 2 from above, even though you can't see it, we know that's true. Okay, then the trickier part, let's see, what is the x value that corresponds to that other endpoint? Well, it's just 1/2 of -1 or -1/2. So when x is -1/2, the y coordinate is f of 2 times -1/2. But 2 times -1/2 is -1. And we know that f of -1 equals -2. And then finally, the largest number in the domain of f of 2x is 1. So when x is 1, the y coordinate is f of 2 times 1, or f of 2. And we know that f of 2 equals 4. Okay, so we plot those points. -3/2, that's -1.5, and 2 is this point. -3/2, 2. The next ordered pair, -1/2, -2. So that's sort of hard to see, but that point is the ordered pair, -1/2, -2. And then the third endpoint that we'll plot 1, 4 is this one, this point. 1, 4, then connect the dots. So the geometric or graphical effect, f of 2x, or the graph of f of 2x, is the graph of f of x compressed horizontally by it's 1/2 of what f of x is. It's a horizontal compression. Okay, let's move on to other examples. So this one says if the base 2 logarithm of x equals capital N and the base 2 logarithm of y equals capital N, then evaluate the base 2 logarithm of 16x to the third divided by the square root of y in terms of capitals M and N. So on this one, we'll first expand the base 2 logarithm of this quotient. So I'll write it out the way that it starts with. The base 2 logarithm of 16x to the third over the square root of y. So we can write this as the base 2 logarithm of 16 times x to the third minus the base 2 logarithm of the square root of y. The square root of y is y to the 1/2. We'll do that in the next step. Also in the next step, we'll write a sum of two base 2 logarithms because we have a product. So when we break apart this one, we get the base 2 logarithm of 16 plus the base 2 logarithm of x to the third, and then minus the base 2 logarithm of y to the 1/2. We can evaluate the base 2 logarithm of 16 because 16 is 2 to the 4th, so the base 2 logarithm of 16 is just 4. And then the base 2 logarithm of x to the third is 3 times the base 2 logarithm of x. And we're subtracting the base 2 logarithm of y to the 1/2, so that's minus 1/2 times the base 2 logarithm of y. And now we can make our substitutions. The base 2 logarithm of x, we're going to replace that with capital M. So 4 stands alone, 4 plus 3 times m. We just replaced log base 2 of x with capital M. And we're subtracting 1/2 times capital N because log base 2 of y is capital N. So this is the desired result based upon the directions. Okay, the next equation involving exponential expressions is pretty easy. 3 to the x plus 1 equals 1 divided by 9 to the x. There's more than one way to do it, but if you notice the common base 3, we can rewrite 1 over 9 to the x as 1 over 3 to the second to the x. So this might be more detailed than is absolutely necessary, but 1 over 3 to the 2x is 1 over 3 to the 2x. And 1 over 3 to the 2x is 3 to the negative 2x. So now we have 3 to the x plus 1 equals 3 to the negative 2x. Since the base numbers are the same, we can say that the exponent x plus 1 is equal to the exponent negative 2x. And then just solve for x. So add 2x to both sides, we get 3x plus 1 is 0. Subtract 1, 3x equals negative 1. And then finally, x equals negative 1/3. Okay, solve the equation 2 times e to the 2x minus 3 times e to the x minus 2 equals 0. This is an equation that's quadratic in form. If you want, it's not required, but if you want to use a substitution like u equals e to the x, then u to the second is equal to e to the 2x. And then you can write down a quadratic equation in the variable u, 2u to the second minus 3u minus 2 equals 0. So I think we can factor this. Let's see what happens. Yeah, if I have 2u plus 1 and u minus 2, I think those work. Okay, so set each factor equal to 0. 2u plus 1 is 0. 2u equals negative 1, and u equals negative 1/2. That's one of the solutions for u. The other one, u minus 2 is 0, or u equals 2. Hey, the goal, though, is to solve for x. So we remember that u is equal to e to the x, and then when we test these two solutions for u, first we'll test u equals -1/2. If we set -1/2 equal to e to the x, we know that this can never happen. This has no solution because e to the x is never negative. So that can never happen. When u equals 2, though, that can happen. So replace u with 2. 2 is equal to e to the x. Take the natural log of both sides, or you could just convert this to its logarithmic equivalent. Either way, you get x equals the natural log of 2 for the solution. That's the only solution to the original equation. Okay, the next equation that we'll look at is a logarithmic equation. So try not to panic on this one. The first thing we'll do is this coefficient 3 will move to the exponent on the argument. So it's log base 2 of x plus log base 2 of x plus 1 to the third equals 3. Now that we're adding two base 2 logarithms, we'll write it as a single base 2 logarithm and multiply the arguments. So this becomes log base 2 of the argument, x times x plus 1 to the third equals 3. Here the goal is to solve for x. We see that x is in the argument of this base 2 logarithm. So we convert this logarithmic equation into an exponential equation. The base number 2 raised to the exponent 3 is equal to the argument x times x plus 1 to the third. Or equivalently, if I just write the argument, x times x plus 1 to the third, that's equal to 2 to the third, which is 8. So this equation is a degree 4 polynomial equation. So we often don't get a lot of practice just finding the solutions to a degree 4 polynomial equation unless we're given a bunch of other information. Okay, but note that 8 is 2 to the third. So think about what number would make x plus 1 to the third equal to 8. So if x is 1, this x is 1, and then 1 plus 1 is 2, and 2 to the third is 8. So by inspection, it's not, if you see something like this, it's probably meant to have a simple type of solution that can be found just by looking at it and thinking about it without expanding that entire x plus 1 to the third. And sure enough, if x is 1, this equation is true. In the original equation, log base 2 of 1 is 0, and log base 2 of 1 plus 1 is 1, right? Log base 2 of 2 is just 1, and 3 times 1 is 3. So x equals 1 is the solution. Okay, I found this on a different instructor's, one of their tests, so I thought it was kind of interesting to look at. Number 8, suppose interest paid on investments at a bank is 3.79% per year compounded continuously. Compute the doubling time on investments. Okay, we're not told about the amount of the investment, but that doesn't matter. We can write down the function. So the amount after t years is the principal. The interest is compounded continuously, with the annual interest rate being 3.79%. So it's A equals P times e to the 0.0379 t. And then we can compute the doubling time. You can use the formula that you might have memorized for doubling time if you have continuous exponential growth like this. Or you can say, well, I'll do it the long way. Find t when a is equal to 2 times the initial amount. So replace a with 2p, set it equal to p times e to the 0.0379 t, and then solve for t. Next, we divide both sides by p. We get 2 equals e to the 0.0379 t. We want to solve for t. T is in the exponent, so we use a logarithm to get t out of the exponent. The natural log of 2 equals the natural log of e to the 0.0379 t, and that's just 0.0379 t. And so the doubling time we get if we divide both sides of that equation by the growth constant. That was the formula I was referring to. The doubling time for a continuously exponential increasing function is the natural log of 2 divided by the growth constant. It's just that when money is involved, we refer to it as the annual interest rate compounded continuously. Okay, the next problem, compute the effective annual interest rate, called the APY, on a bank account if the nominal annual interest rate is 4% compounded continuously. Okay, so the idea is if you're told that your account is earning interest at 4% per year compounded continuously, you're actually making more than 4% per year because of the compound interest. You're earning interest on interest while the year is still underway. So that is called the effective annual interest rate. So we set it up the same way. A equals P times e to the 0.04 t. But this can be thought of as P times e to the 0.04 raised to the power t. And then if we use a calculator to come up with a decimal approximation for e to the 0.04, then we can make this look like a compound interest formula if interest is compounded once a year. And then we can identify what the effective annual rate is. Okay, so I'll use a calculator to get a decimal approximation of e to the 0.04. Okay, so I get A equals P times 1.040810774 raised to the exponent t. So remember the interest formula, if you compound it once a year, it's A equals P times 1 plus R to the T. So the number that we're adding to 1 is 0.0408. So this is a little bit bigger than 4% per year. So you could say that the effective rate is about 4.08%. Okay, next problem. Another logarithmic equation. Log base 7 of x minus 2 plus log base 7 of x plus 4 equals 1. So the first thing to do, since we're adding two base 7 logarithms where their coefficients are already 1, we can write this as a single base 7 logarithm if we multiply the arguments. So we get this equation. Log base 7 of x minus 2 times x plus 4 equals 1. And just like we always do, we transform the logarithmic equation into an exponential equation. The argument x minus 2 times x plus 4 is equal to 7 raised to the first power. This is a quadratic equation, so we'll solve it using one of our methods. So we'll subtract 7 from both sides. We get x squared plus 2x minus 15 equals 0. And this factors pretty nicely. One factor is x plus 5. The other one is x minus 3. The quadratic equation has two solutions. One is negative 5. The other one is positive 3. We can tell already that negative 5 cannot be a solution because it makes the arguments negative. So negative 5 is not a solution. X equals 3, that looks like, yeah, that's going to work. So log base 7, 3 minus 2 is 1, so log base 7 of 1, and then plus log base 7 of 7, because 3 plus 4 is 7. Log base 7 of 1 is 0, and log base 7 of 7 equals 1 is true. So x equals 3 is the only solution. Okay, let's sketch a graph of y equals e to the x minus 2. So you might want to sketch y equals e to the x first. On this function, we know that y equals 0, which is to say the x-axis to the left of the y-axis is a horizontal asymptote, and the ordered pair 0, 1 is the y-intercept, and the graph has this shape. And then the graph of y equals e to the x minus 2 is the graph of y equals e to the x shifted vertically down 2 units. So you have to make sure that you identify the horizontal asymptote, y equals negative 2. This point, 0, 1, gets shifted down 2 units. So the y-intercept of this function, y equals e to the x minus 2, the y-intercept is 0, negative 1. 0, negative 1. And then there is an x-intercept. So we need to identify the x-intercept. So that's not too hard. Every x-intercept has a y-coordinate of 0. So in this equation, we replace y with 0 and then solve for x. So if 0 equals e to the x minus 2, add 2 to both sides, 2 equals e to the x. And then the natural log of 2 equals the natural log of e to the x, which just simplifies to x. So the x-coordinate of the x-intercept is the natural log of 2, if you can read that. Okay, we have time to do at least part of this next example. Let f of x be equal to this rational function, negative 4x plus 6 divided by negative x plus 2. There's a vertical asymptote. So the x value that makes the denominator 0 is x equals negative 2. So the vertical asymptote is x equals negative 2. And there is a horizontal asymptote. The degree of the numerator is the same as the degree of the denominator. And then the horizontal asymptote is the leading coefficient of the numerator divided by the leading coefficient of the denominator. And negative 4 divided by negative 1 is 4. So the horizontal asymptote is y equals 4. And then the y-intercept, when x is 0, replace every x with 0, we get 6 divided by 2, or 3. And then to find the x-intercept, well, for a rational function, just set the numerator equal to 0 and solve for x. So if we add 4x to both sides, we get 6 equals 4x. Then divide both sides by 4. X is 3/2. So the x-coordinate of the x-intercept is 3/2. The y-coordinate is 0. Okay, it's 10 minutes till, so I told you earlier that I'm supposed to give you an opportunity during class, the last 10 minutes, to log into Moodle and do the course evaluations. So that's what we'll do now.